Each of the conics is formed by the intersection of a plane and a right circular cone. If the plane passes through the cone parallel to the base, the result is the very familiar circle. If the plane passes through the cone at such an angle that it completely cuts through one nap of the cone, the resulting conic is called an ellipse. An ellipse. Now, if the plane passes through the cone at an angle parallel to the side of the cone, the result is the ubiquitous parabola. And if the plane passes through the cone such that the acute angle formed by the plane and the base of the cone is greater than the angle formed by the sides of the cone and the base, the result is called hyperbola. Note well that each cone has two naps, and consequently, each hyperbola has two branches. These are the conic sections. Know them well. Circle, ellipse, parabola, hyperbola.
Circle, ellipse, parabola, hyperbola. Circle, ellipse, parabola, hyperbola.
Yes, Mr. Gale, what is it?
Professor McConicle, why do we have to learn all this stuff? What possible relevance will it have on my future?
That's important. introduction of meat into the early hominids' diet caused a smaller gut, which also increased brain size. This is an important moment in our history. That's important.
And behind the sun. This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't. In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks, called equation clocks, were made that would do this for you, but eventually, we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing
that
up.
resembles a figure 8 is called an analemma. It traces the continuous path of the sun over the period of 1 year. The analemma's unique shape is the result of two unique properties of the Earth. The Earth's axis of rotation is tilted 23.5 degrees relative to the plane of the ecliptic. This tilt results in a perceived up and down, vertical, motion of the sun when viewed from Earth. The shape of the Earth's orbit is elliptical, and this causes the rate at which the Earth orbits the sun to vary. The left and right motion, the distance from a vertical center line, is the result of this changing rate. If the Earth's orbit was perfectly circular, the analemma would become a vertical line. Further, if there were no tilt in the axis of the Earth relative to the plane of the ecliptic, and the Earth had a circular orbit, the sun's position would not change in this door and dash. It would appear in the same location each day at noon. Location description: Golden, Colorado.
Layout of the solar system. The planets closest to the sun move faster and the outer planets move slower, but they all go in the same direction. Apparent retrograde motion is when the planets appear to temporarily change the direction of their orbit. They don't change direction, it just looks that way from Earth. It's an illusion that unfolds over a matter of weeks or months. In this image, Mars was photographed every 5 to 7 days between October 2011 and July 2012. Once all the photos were combined by aligning the stars in the background, it appears as though Mars looped back on itself before continuing on its orbit. A retrograde illusion like this happens when we lap an outer planet like we do with Mars every 2 years, or when an inner planet laps Earth like Mercury does every 4 months or so. But for both Mercury and Venus, the illusion is hard to actually capture, since they're located on Earth's day side, not on our night side. When those planets are visible, it's only right around sunset and sunrise. But assuming you could see it, here's a diagram of how the Mercury retrograde illusion would work. This line shows our view of Mercury against the background stars. As Mercury passes us by, our line of sight shifts so that for about 3 weeks, Mercury will appear to loop back on itself when viewed from Earth. It's simply a function of two objects orbiting in the same direction at different speeds. If you stood on Mercury, you would see Earth make an apparent loop too.
Isaac Newton, I mean, just look at, you read his writings. My hair stands up on, I don't have hair there, but if I did, it would stand up on the back of my neck. You read his writings, the man was connected to the universe in ways that I've never seen another human being connected. It's kind of spooky, actually. He discovers the laws of optics, figures out that white light is composed of colors. That's kind of freaky right there. If you take your colors of the rainbow, put them back together, you have white light again. That freaked out the artists of the day. How does that work? Red, orange, yellow, green, blue, violet gives you white. The laws of optics, he discovers the laws of motion and the universal law of gravitation. Then a friend of his says, well, why are these orbits of the planets, why are they in the shape of an ellipse, sort of flattened circle? Why aren't they some other shape? He said, I don't know. I'll get back to you. So he goes home, comes back a couple months later. Here's why. They're actually conic sections of a cone that you cut. And they said, well, how did you find this out? How did you determine this? Well, I had to invent integral and differential calculus to determine this. Then he turned 26. Then he turned 26. We got people slogging through calculus in college just to learn what it is that Isaac Newton invented on a dare, practically. So that's my man, Isaac Newton.
Okay, we're going to make another journal entry. So remember, it was just 2 blank pages of paper that we folded in half. And our first entry was conic sections. And our second one is going to be on our second page. And that's going to be topics in calculus. And there are 3 topics in calculus. And they are limits, derivatives, and antiderivatives.
The first one is going to be a limit. And all a limit is, it asks, what y value? What y value do we get close to? Get close to as we approach or get close some x value. But the answer is the y value. That's the answer. As you get close to some x value, and they just want to know what y value you get close to. The second topic is called the derivative. And a derivative is a function which measures slope. And the slope is going to be found at some x value. There's a whole bunch of different ways to let people know that you're taking the derivative. You can say f prime of x. You can say y prime. You can say dy dx. You can just say d dx. Another way is capital D, little x. Sometimes whatever the function is, they'll wrap it and then put the prime after it. There's all kinds of different ways to let people know you're taking the derivative. So far we have a limit, a derivative, and then the third one is called the antiderivative. It's also sometimes called an integral. And it's that thing that looks like a big S. Looks like a big S. And this is a function which measures area. I'm not going to say area, I'm going to actually say net area. And what that means is sometimes you can get a negative area. So it's the net area between a function and the x-axis. And this here, the antiderivative, is why calculus was invented, in order to find the area of non-standard shapes such as the ellipse.